This is Aidan Toohey from EPRI. Welcome to this afternoon's webinar. I'll introduce the webinar I'm going to host, and Niall Dowell is going to be presenting on the topic, today's topic of electrification and industrial sources of system balancing flexibility. For those of you who've seen Niall's bio on the website, you can tell he's got a lot of experience in this area. He's a professor at energy systems engineering at Imperial College London. He's widely published in the area, molecular level, unit operation, integrated process, and system scale. So he's able to give a good sense of the issues here and how we can leverage some of these new resources and some of the challenges of doing so. Niall's got over decades experience as a consultant to public and private sectors on lots of various committees and members of advisory boards. So Niall's going to talk today about this topic of electrification and industrial sources of flexibility. I will just make folks aware that this is related, and Niall is the technical lead together with myself on a task force, an ESIG task force on this topic of electrification and industrial flexibility, and it's one where we're putting together, working on the final touches on a paper on the topic to try and identify what some of the issues are when you think about these types of resources to support energy systems integration. So that paper and associated slide deck should be coming out here in the next few months. Niall will talk about the actual group that we've put together to support that paper. In terms of the logistics of today's webinar, everyone is muted on entry, and so you won't be able to speak up to ask questions. The way we've been trying to get questions on these webinars, for those of you who've been on here before, is slido.com. You can see on the slide here, go to slido.com, enter ESIG 21. And then you can submit questions. The advantage of using Slido is that we can vote questions up and down. So please do vote the questions you want to be asked. We'll hopefully have 20 or so minutes right at the end here to get into a discussion and look at the questions that people are asking. So do ask questions, provide comments through the Slido platform, and we can get to those at the end of the presentation. Other than that, I guess now I'll turn it over to you and you can go through the slides, but I appreciate everyone joining today. Thanks.
Thank you very much, Aidan, for the kind introduction, and thank you everyone for your attention and attendance here this evening or this morning or this afternoon, wherever you happen to be. I'm currently based in London, so good evening. As Aidan said, I have been contributing to this study along with himself and a number of other colleagues focused on this. My background is chemical engineering as opposed to perhaps electrical or electronic engineering. So I'm coming at this question with that mindset and that framing in mind. So that's what I would like to sort of discuss for the balance of the time here today. Without any further ado, I want to just sort of jump quickly on. And so I'm going to go through a fairly standard outline. I mean, the key point really is that, as Aidan said, we are part of a team who are performing this broader study for ESIG. So really, I want to emphasize that I'm delivering a study, but it's been very much a team effort, and we'll go through who was part of that team in a moment. I'll also detail a little bit on the background and scope of the broader study and what I'm going to try and talk about. And then for the balance of the time, I'm going to focus in on thinking about the way in which the energy intensive industries can be part of this grid balancing and flexibility piece, which inherently implies their electrification. So what I'll be talking a lot about here will be, the challenges and opportunities and ways in which A, the EIIs can be electrified, and then B, the possibilities for those electrified in industry sectors to in turn interact with the electricity grid and provide the various services that are required.
Hey, Niall, you're pretty low there. I don't know if you can move that mic a bit closer or somewhere.
Okay. Is that any better?
That's a lot better, yeah.
All right. Thanks, Aidan. And then the next thing that I want to talk about briefly will be the way in which hydrogen will potentially interact in this space. And again, there's a lot of discussion. So again, I want to bring a sort of systems engineering perspective to this and the way in which hydrogen may interact with an electricity or energy system that will increasingly rely upon resilience and flexibility services to ensure that. And then finally, I'll present some of the conclusions of the study so far. So taking just a very big step back, since the 2015 Paris Agreement, more and more countries and indeed corporations around the world have started to commit to net zero targets. So whether it's places like the UK or the EU, where we have legislated targets for net zero emissions by 2050, or in China where it's 2060. I mean, this is pretty significant. And then increasingly, whether it's oil companies or insurance companies or large tech, net zero is becoming, an increasingly normal part of the transition paradigm. Importantly, individual US states have also started to make their own commitments to reduce CO2 emissions, again, via a range of approaches. So some of these approaches imply increasing significantly the amount of intermittent renewable energy, so wind and solar power. Others are thinking about banning certain types of technologies or incentivizing others. So again, there are many ways to achieve this, and everyone seems to be going about getting to this end destination of the sort of the Paris Climate Agreement in their own way. More generally, increasing the electrification of the broader economy. So whether this is electrifying the heating system or the mobility sector or the industrial electrification, as is the subject of this talk, this is an increasingly important part of the broader decarbonisation effort. And so in that context, with that in mind, it's increasingly accepted and understood that this means that the electricity system and grid needs to be increasingly flexible. And by that we mean able to promptly respond to quite significant swings in demand and to be resilient as it does so. So there are a range of mechanisms for providing this kind of flexibility. So for example, this could be demand side response at the domestic, commercial, or industrial level. You could also have deployment of energy storage options. So again, as we know, energy storage goes from the sort of flywheel level through the battery level up to the power to gas, power to methane, power to hydrogen type grid scale interseasonal duration storage. So a whole portfolio of solutions here. And also, for example, carbon capture and storage, CCS, applied to thermal power plants can also provide flexibility in a carbon constrained environment. Importantly, I think the role and value of each of these flexibility mechanisms, it will vary as a function of the broader landscape. So this includes everything from the respective prices of various fuels, so coal, gas, biomass, oil, and so on, but also the availability of wind and solar power, so wind speed, solar irradiance, and so on, the qualitative shape of the load duration curve, so how, what's the differential between peak and trough load, and so on. So all of these things come together to inform and influence the demand for flexibility services. So the context for this study is one where we have extensive deployment of intermittent renewable energy sources. So again, the wind and solar power, or existing sources of flexibility. So for example, current battery technology or pumped hydro storage, this kind of thing, may no longer be sufficient. We recognize in practice that this will be really a region-specific set of answers, so there is no one-size-fits-all answer. However, we have tried to remain as region agnostic as possible and to try and stay reasonably high level and try and present some general insights. So as I said, the balance of this presentation focuses on the energy-intensive industries, and I'll get into what that means in a little bit more detail in a moment, and also the way in which hydrogen may also play a role here. So maybe just to start, grid priorities are evolving. So if we think about the grid in the 20th century, and this is indicated, maybe just to check, can people see my mouse, my cursor on the screen when I'm moving?
Do not, I think, now today.
No, okay. So you can see in this figure in the middle of the screen, on the left-hand side in gray, this is a sort of a cartoon of the sort of the 20th century paradigm, where it was characterized by more or less homogeneous, large, centralized electricity system, where you've got all the kinds of power plants that you have, they're all burning something, whether it's coal, gas, oil, uranium, biomass. They're producing, in some cases, a lot of CO2, and you've got a centralized decision maker. So and importantly, they all provide more or less the same sort of portfolio of grid services. In the paradigm, in one potential paradigm to which we're evolving, or toward which we're evolving, we have an increasing amount of intermittency, a much more decentralized grid with many more small generators, and increasingly a move from consumers to prosumers, so much more consumer engagement and consumer involvement in the energy system. And also we are in an increasingly CO2 constrained environment. So in that context, instead of having a world where we compete more or less exclusively on short-run marginal costs, and efficiency is king, what we've started to observe is that the value of efficiency in some markets is in fact declining. And what's actually much more important would be reductions in capital cost and maximizing the flexibility or dispatchability of a given technology. And so, for example, here we defined flexibility as the time it takes to go for a given technology to go from its minimum stable generation to its maximum stable generation, or in the context of energy storage, being able to charge and discharge quickly. The other option that becomes the other aspect that becomes very important is the ability of the technologies to provide all of the requisite ancillary or grid services that are required to make sure that the grid is itself resilient. And I'll go into a little bit more detail of what those are in a moment as well. And then finally, what's also very important is the ability of the system that a given country or region has the capability to deploy at scale the technologies that are required to make the grid work. There's no point in postulating any sort of perfect unicorn technology if fundamentally the capability to deploy it simply does not exist. We don't have the technologies, we don't have the supply chains, and so on. So all of these things come to bear. As I mentioned, the electricity system, it requires a range of services, and some of these are indicated here. So for example, frequency balancing systems, so inertia, primary, secondary, tertiary response, but also things like system strength and reserve power, and then the ability to restart in the case of a black restart, for example, and then finally reserve capacity. So depending on whether this is contingency or load following reserve and so on. Importantly, even within a conventional system where we've got nuclear power, bioelectricity, gas turbines of different kinds, coal power, bioelectricity, wind and solar, pumped hydro, or batteries, not all technologies provide the same suite or same portfolio of services. And thus, when assembling a grid portfolio in the future, we need to think about this in a much more focused way than we did historically. Where the topic of today's conversation comes in is that, for example, additional services beyond what are shown on the table here can include things like demand side reduction or demand side response, so DSR. And this is one thing that can be provided. This is one service that can be provided by, for example, the energy intensive industries. Other options could be things like frequency balancing. And again, we'll speak to that later. So to pause and to talk about the team that helped pull this paper together so far. So it's quite diverse. So Aidan from EPRI, myself from Imperial College, but also Elizabeth Endler from Shell, Julian Beer from Anglo American, Perluigi Mansarella from the University of Melbourne, Julia Metosavan from ERCOT, as well as Connor Anderson, also from ERCOT, Anthony Koo from NICE, Marta Hugo from Konkawa, Eshan Shafi from Konkawa, William de Hasseler from KU Leuven, and Toby Price from AMO. So again, a very diverse mix. We've got folks from academia like myself, but also other research groups like from NICE, industry groups from Konkawa, as well as the oil and gas sector from Shell, electricity grids and ERCOT, and Julian, for example, from the iron and steel industry. So a very broad portfolio of perspectives being brought to bear here. So shown here on the left is an infographic describing or enumerating what we might consider to be the energy intensive industries, and then on the right, sort of an indication of the way in which all of these industries are enmeshed with the broader economy, but also with each other. So their individual supply chains are intertwined, and they're not only is the decarbonisation of these individual point sources of carbon, but also that has to happen in order to transition to a low carbon economy. But similarly, the products that these sectors provide will also be valuable in the context of this transition. So addressing the decarbonisation through, for example, electrification of the energy intensive industries is really key. Importantly, the energy intensive industries were profoundly impacted by the recent, or the decade ago now, the economic crisis. So again, this has been really challenged. And so their ability to spend capital money is limited. Importantly, most energy intensive industries already see recycled materials as important elements in their supply chain. So this is sort of something that's happening now. And the business models that are associated with, for example, steel are evolving. It's important to note, again, this is a very European context, but they've already played a pretty significant role in reducing emissions. So for example, in the period 1990 to 2015, EIIs reduced their emissions by about 36%, representing approximately 28% of economy-wide reductions. And this is despite the fact that they were responsible for only about 15% in 2015. Now, unfortunately, a lot of that has come about through partially a combination of energy efficiency and fuel switching, which is good, but a lot of plant closures and reduced outputs, partially because of the financial crisis that I mentioned earlier, but also just through a sort of offshoring of emissions as well. So without wanting to offshore everything, because let's agree that that's possibly not ideal, there are other ways that we can achieve further emission reduction. So for example, further efficiency improvements where possible, but also, and this can be done through, for example, process integration, heat integration, that kind of thing, electrification of heating and various processes, the incorporation, so again, fuel switching to switch from unabated natural gas to blue or green hydrogen. So that's blue hydrogen derived from methane, green hydrogen derived from water electrolysis, and then the use of carbon capture and storage technologies. So importantly, electrification is not, it's useful. It's certainly something you can do in many cases, and it has different potentials in different sectors. So for example, you can see here that steel could be, could have a high potential for electrification, and indeed it does already apply this technology quite significantly. But then, for example, the paper sector or the lime sector has a much lower potential here. So it's possible, but it's not the main route, no indication of wide scale application just yet. Importantly as well, not all of these routes are mutually compatible. So we can't obviously do electrification and hydrogen and carbon utilization and fuel switching and so on. There are limits. So for example, you can't do everything everywhere. So in some cases, electrification is already quite widely applied, as I mentioned. So for example, in secondary steel making, but in others like cement or maybe refining, it's at best a partial solution. So for example, owing to the intrinsic CO2 emissions associated with the calcination of limestone, those emissions cannot be abated via electrification. So again, and this is one of the real challenges in decarbonizing the industrial sector, is its heterogeneity. There's almost no such thing as a standard plant. So one of the key challenges next is to start thinking about the quality of the heat that can be provided via electrification. So when you're talking about low quality heat, or low temperature heat, so that's anything roughly below about 300 degrees Celsius, that can be relatively easily provided. So whether it's electric arcs or microwaves or so on, this can be delivered that way. However, at higher temperatures, so you're getting into sort of more than 1,000 degrees, and you need this if you want to produce cement, for example, getting this via electricity is more challenging. So electric arc furnace technology does exist, but it's currently at a relatively small scale, and it would require further adaptation for deployment in some of these industrial contexts. And that's an important technical and thus financial challenge. Importantly, all of these industrial processes, any given industrial facility they tend to be very highly integrated. So any process element, any alteration to a given process element, it will have knock-on implications to the rest of the process, which could in turn have capital or indeed maintenance and operating cost, if not safety implications. So this is not something that's undertaken trivially or simplistically. So something that's going to be really important will be the progression of technologies to TRLs above 7. And what's really important if you want to start using more electricity in the industrial sector is the further decarbonization of the electricity grid. Quite frankly, in most parts of the world, we're simply not at a stage where electricity is a plausible option for the delivery of decarbonized solutions. It needs to be much more deeply decarbonized for it to be a plausible option relative to credible counterfactuals in the near to medium term, I think. What's also really important is that, regardless of when we do this, any effort to electrify EIs will very significantly increase the amount of electricity that needs to be generated in that given region. So for example, if we think about Europe, this could be between 2,900 and 4,400 terawatt hours per year. So this is a very significant amount of electricity relative to the current installed base. And what's important is that this power must be available in a very reliable way, but it also has to be very affordable. These industries are already price challenged. And finally, that electricity must be itself deeply decarbonized, if not fully renewable. So to that end, it's likely that the energy intensive industry sectors and the electricity sector may well co-evolve and evolve to become much more intertwined and closely integrated than they currently are. So what that means is that given that flexibility services will become more and more valuable as time goes by, quantifying and qualifying the role and value of the flexibility services that EIIs can provide will be important. Importantly, the demand for electricity or energy that industrial facilities typically present, it's base load. So this is not obviously compatible with power supplies, which have a very significant integration of intermittent renewable energy. Wind and solar power do not by themselves provide baseload power. So therefore, we need to think more about how the EIs can contribute to the resilience of such a system. What we're looking at here on the left-hand side is the amount of electricity that's currently used in terms of the energy footprint of any given facility, right? And so what you can see here is that, for example, if you're in the cement or glass sector, about 14% of the energy use comes from electricity. But if you go to aluminium production, for example, it's as much as 65%. So again, this sort of serves to reiterate and to re-emphasize the way in which different sectors will be able to use more or less power. One option, or in general, electricity is used for example, machine drives and process control and also the direct provision of feed. This machine drive piece is important because again, you're talking about having potentially large rotating masses which have the possibility to provide electricity grid services. So the other challenge is that incumbent fuels are relatively cheap, and natural gas costs are often particularly hard to overcome with direct electrification, as it also often has higher operating costs. Similarly, own fuel use, so fuel that's produced during an industrial process and subsequently used, that tends to be very, very cheap. So for example, if you have a blast furnace gas that's produced during the production of steel, that's typically recovered and reused as a fuel. So sacrificing that and then instead using it as using electricity, which has to be bought as an energy source, will increase costs. Fuel switching is not free of capital cost either, and there are existing regulations and policies in pretty much every jurisdiction that likely favor one fuel or one approach over another. The other piece is that electricity infrastructure costs has its own set of constraints. The infrastructure that exists to deliver electricity to a given site has its own set of not only costs, but also constraints. And finally, there is a level of risk aversion that needs to be borne in mind in the industrial sector. Moreover, we need to have an availability of electric process equipment in that industry, and there isn't necessarily sufficient knowledge or capacity to redesign manufacturing process lines and to integrate those systems. As I mentioned before, the industrial sector is characterized by profound and pronounced heterogeneity, so almost no two facilities to produce ammonia or cement or steel are the same. They all evolve and change depending on local conditions and regulations and practices and feedstocks and so on. Higher temperature processes, simply due to their higher energy costs relative to industries with lower process temperatures, are often found in low margin sectors. So for example, steel, iron and steel, cement and glass. So if intermittent renewable electricity is used, then low cost power may only be available for some hours of the year during times of overproduction. So for example, when you would have curtailment, or perhaps during low overall demand. So for example, in the middle of the night or something like that. So this means that process equipment capacity factors could be low, or you need additional investment in energy storage. So this will inherently drive up the cost of production and will also require more flexible modes of operation with potentially modified equipment designs. And all of this is starting to introduce more and more risk to your industrial facility from a technical and financial perspective. So challenging. So from the literature, we've observed that the various CIIs could provide a range of grid services, so including frequency regulation from variable frequency drives or non-spinning reserve from electrolytic processes and electric arc furnaces. So this is possible, and it has been demonstrated it's been observed and discussed in the literature quite extensively. And then, for example, EPRI have done quite a lot of work in this space, and they've evaluated the impact of industrial electrification on the electricity grid, and their most aggressive scenarios indicate that this could increase from a reference scenario. So the electricity share of industry could increase from about 27% today to about 40 to 45% in the future. So this is a very significant increase in electricity demand. So if we assume, for example, and again, we're moving back to the EU context, that all electrical technologies for heating and electrolysis are provided via electrothermal tech, and that's used for material separation. We use that across the EU. This could be a fourfold increase in electricity demand by 2050. So that's a vast amount greater than what we use today. If we try to replace fossil fuels with hydrogen, CO2, and syngas, electrolytically provided, that involves nearly 10 times more electricity by 2050. So again, this does not come without very significant infrastructure challenges. And finally, as discussed by Palm et al., the implications of, for example, trying to electrolytically produce plastics in the EU would not only require between 14 and 1900 terawatt hours of power per year, but it could also increase production costs by about 300%. So none of these are trivial challenges. They're very significant. Changing tack slightly, and to speak about hydrogen for a moment. So if we think about just the origins of so-called green or electrolytic hydrogen. So this was actually first demonstrated in the 18th century, in 1798, by two Dutch merchants, whose names I'm afraid I'm not going to try and pronounce here, but they used an electrostatic generator to produce an electrostatic discharge between two gold electrodes, which were immersed in water. And it took about a century later for this concept to make it out of the lab and be demonstrated in industry. And it was Dmitry Lechinov was the first to do this. And by 1902, more than 400 alkaline water electrolysis units were in operation around the world. And by 1920, this technology had been brought up to the 100 megawatt scale, primarily used for the production of ammonia fertilizer in Canada and Norway, owing to the low-cost hydroelectricity that was available there. So again, this is not really a very new technology in that context. So over the course of the last century, so since 1920 to 2021, various hydrogen hype cycles have come and gone, and often fueled by promises of too cheap to meter electricity and so on. Back in the 1950s and thereabouts, we were going to get this free power from nuclear power, and now potentially it could come from renewable energy. So again, this idea of cheap energy, cheap hydrogen has, it's been there before. Hydrogen as an energy carrier is beguiling. So it can, in theory, it's a fantastic energy carrier. We can use it to provide heating, power, mobility. So believe it or not, this in the bottom right-hand corner is a hydrogen-powered Humvee truck, and all of these technologies are available today. The challenge is that the demand for energy services has very limited elasticity, and it's quite time sensitive. So the value of lost load is too great. So we need to be sure that we can have the power of the energy service that we need when we actually want it. So if we think about, the curtailed renewable storage, so how much hydrogen, how much renewable energy can we get for free, as it were? So what we're looking at here on the left-hand side, so on the x-axis of this figure, you have the percentage of total capacity of renewable energy penetration, so wind and solar penetration into a given grid. These calculations were done in the context of the UK grid, but I think the general point is general. On the primary y-axis, you're seeing the curtailment available as a potential of available renewable power, and what you can see here is that it's not until penetration becomes very, really quite significant, much greater than about 50% of total capacity, then curtailment starts to become meaningful in the UK context. And then on the secondary y-axis, you can see what this translates into in terms of terawatt hours per year. And the key point here is that it doesn't look like curtailment becomes a meaningful fraction of some of those many thousands of terawatt hours that we saw that we needed for the industrial sector on the previous slides. So curtailed electricity is likely going to be something of a red herring in my view. And again, this is exclusively my view. And the key point really here is that if what you want to do is use curtailed electricity to, for example, produce hydrogen, this will result in a very low capacity factor. Well, what does that mean? So we're thinking about here the impact of a capacity factor on hydrogen costs. So on the left-hand side, you're looking at where we're assuming a fixed electricity price of $40 per megawatt hour. And then each of the colored curves corresponds to a different electrolyzer price. And what we're then saying on the primary y-axis is the cost of hydrogen in US dollars per kilo as a function of the number of hours during which your electrolyzer is able to run. And so, you can argue about the validity of the $40 a megawatt hour. You can argue or debate the viability of the electrolyzer price range that we're looking at here. Certainly they're quite low at the low end, but the point remains that, unless your electricity is available basically all the time and you're running full load, it's very expensive. And moreover, it's understood that hydrogen needs to be available at less than about $1 a kilo in order to be viable as a means for producing electrofuels or hydrogen fuels. If we think about here where we fix the capex, so this is the right-hand graph, we fix the capex as for $50 a kilowatt for the electrolyzer. And again, you're looking at the price of hydrogen in dollars per kilo of hydrogen on the primary y-axis, and again, full load hours. And again, we're looking at the cost. You can see that we need to get to a world where we have more than 4,000 hours a year of free electricity before we get to that $1 a kilo cutoff point. So assuming that this is deliverable via curtailed renewables that's quite a brave assumption, I think. So we will have to pay for electricity. Obviously, there are a range of options for providing grid flexibility via electricity or energy storage, and hydrogen can play an important role via what's called power to gas or power to gas to power. So you take the electricity, you convert it to hydrogen, you store the hydrogen, you take the hydrogen back out of the system, the storage system, and we use it to generate power again. So this is this so-called two-way coupling of hydrogen infrastructure via, for example, you could have an electrolyzer, your hydrogen storage your hydrogen storage facility, and a fuel cell. However, and conceptually this it's quite appealing, right? But whilst it might represent an optimum long-term role in supporting flexibility, and this importantly remains to be proven, there are reasons to believe that the path to this end state may evolve in an uneven manner. So rather than just read this to you, because it's quite a dense page, the key point is that if you think about the cost of electrolyzers, PEMs, so say 100 megawatt PEMs, they're about, say, $1,300 to $1,600 a kilowatt. And by 2030, the aims are to get them below, say, from $390 to $480 a kilowatt. Fuel cells are potentially, more expensive, right? So right now they're $1,100 to $1,400 a kilowatt, but it's anticipated that by 2030 they'll get to $850 to $1,000. So still quite a lot more expensive than the PEM electrolyzers. So if you then think about what this translates into in terms of a dollar per kilowatt option, you then find that the bidirectional storage system, the fuel cell contribution to costs, accounts for about 40% of total capex, but would grow to 60% owing to the smaller expected or reduced expected levels of improvement. In contrast, the unidirectional, so the power to gas to something else, only withdraws electricity from the grid during peak production, and it could see cost reductions of 70%. So that's very significant. So of course there are issues downstream that are important, but the implication is basically clear. If cost reductions follow a sort of qualitative expectation, the attractiveness of withdrawing power during peak production periods could see faster improvements relative to returning it during trough production. So the use of hydrogen to provide flexibility doesn't have to be bidirectional immediately. And an alternative to the integrated hydrogen energy storage solution could be a more dynamic arrangement where pockets of unidirectional flexibility develop as separate localized operations that coordinate via, for example, market signals. So you could have electrolysis during peak production, for example, to reduce curtailment, as well as system-level demand response options. So again, this is where the hydrogen piece, coupled with the electrification of energy-intensive industries, could work together. So this might provide a more achievable path towards the use of hydrogen for flexibility services, as opposed to an integrated solution with some relatively expensive parts. So some conclusions at this stage of the study, and I would emphasize at this point that we're not quite finished yet, but flexibility isn't anticipated to become increasingly important as decarbonisation efforts progress. However, the role of electricity or energy-intensive industries and also power to gas to power hydrogen in providing this service, it's far from straightforward. And the EIIs are deeply enmeshed in the economy, so we have to be very careful about how how any change in that sector will have implications elsewhere. And it's also important to recognize that EIIs tend to be quite trade exposed. So we need to take that into account. So also importantly, the decarbonisation, therefore, of the industrial sector, it sits at this nexus of energy policy, industrial policy, trade policy, climate policy, and perhaps even industrial strategy if your country has one. So this is, again, very complex. We need to be aware of the very substantial increase in demand for power that goes along with the electrification of energy-intensive industries, and it's not obvious yet that this route will be even close to cost neutral. You recall a while ago when I mentioned a 300% price increase of the plastics, for example. There was some evidence for the extent to which EIIs can provide good services, but this could result in profound and significant changes in the way in which those industries operate. And it's not obvious if these ideas are practicable at large scale. Some more conclusions. So electrolytic history has a very long and storied history. As I mentioned, it goes back to the late 1700s. And the concept of storing so-called otherwise curtailed power in electrolytic hydrogen, it's a persuasive and certainly pervasive concept, particularly in the inorganic chemistry literature. But I mean, first of all, you need a very, very large deployment of renewable energy before material amounts of curtailment actually emerge. And then owing to the very low capacity factors that you would get if you just tried to run this, it's a very, very process. It's going to be a very costly process. And of course, by the time by the time that you start to buy the electricity from these grids, it's no longer free. You now have to pay for it. You're not going to get it for free. So it's not obvious. So A, that's one thing. And then B, it's not obvious that the two-way coupling of hydrogen production is optimal. So it might make more sense, given the more multi-sector integration that we anticipate in the future. It might make more sense to turn potentially curtailed and just generally electricity into hydrogen, and then pass that hydrogen to another sector of the economy. So for example, the mobility, so the transport sector, and that might be more cost effective. So I think the key point, and the point on which I'd like to end, is that there is certainly ample space for future work for anyone who wants to get involved in this area. So with that, I'll pause, and I guess, Aidan, we can try and move to some questions. Thank you very much all for your kind attention.
Thanks, Niall. Much appreciated. A lot of good food for thought there. And as we mentioned at the start, this is a lot of the material being discussed will be part of the paper that we're putting together, obviously, and the feedback today I think can be used to kind of sharpen some pieces as well, which would be good. So yeah, there's quite a few questions coming in on Slido. I'll ask folks to go on to Slido if they have more questions or comments that they want raised, and vote on the ones that are there, because we'll go from the ones that are getting the most votes. And I think you can vote on your own question as well if you want to push it off. The first one here, which segments or sectors of the industry already have low utilization, and how flexible might that be to be shifted daily or seasonally? So what are the kind of sectors that might be useful resources to provide some of the flexibility that's there?
So I'm not entirely sure if I can really answer that question, but my understanding is that, most energy intensive industries try to avoid scenarios where they have low flexibility. And whenever I found myself in a context where I've been thinking about or discussing flexible operation of, an integrated chemical plant or something like that before, people generally didn't like the idea on the basis that, these systems are not designed to operate flexibly, and they're not intended to be controlled in that way either. So I think that the amount of the extent to which utilization can be shifted daily or even seasonally is low and will come at some significant cost.
Okay, that's interesting. The next question, kind of jump into the hydrogen aspect. So you had mentioned that there's a thought out there that it would be using curtailment or otherwise curtailed renewables to operate the electrolyzers. I think the point being made that really the operation of electrolyzers would be a function of electricity prices and not necessarily curtailment. And have you looked at that? I guess seems like there was some study work you showed there, some of those examples, but within that, is that looking at kind of the hourly variation in prices, that type of thing, that would be important there?
No, so I completely agree with Russ's point here. I think it will absolutely be a function of electricity prices, and I guess what I was responding to or reacting to more in my own remarks was what I have tended to see at conferences and so on, where this assertion of free or indeed negatively priced electricity being used to produce hydrogen and thus provide, options for producing so-called electrofuels and so on. This is something that is proposed as an idea. I agree with Russ's assertion here. Have I looked personally at future price distributions? Not in this study, no.
Thanks, Russ. The next one, going back to the industrial energy intensive industry. So around the participation in reserve markets and energy markets, I guess. Are those actually participating right now? I guess we know of some demand response type products that are used in various markets, and any sense of how much that's likely to change. But particularly, I think the reserves aspect might be interesting, because obviously you can kind of bid in and not get used all the time. It's a few times a year. Is that something that you've heard folks talk about, being able to provide some of that if they get paid enough, obviously?
Yeah, so I can only really comment about this in the UK context, but the amount of demand response that our industry sector can provide is relatively small. So it's small both in the number of megawatts, but also in the number of megawatt hours. So it's not a huge amount. With more electrification, I mean, it potentially could go up in volume, but again, it just depends on the extent to which these, you're getting into a world there where I guess you're sort of hoping that you'll be paid more for not producing, and thus you can get paid for not consuming the electricity, as opposed to the value of the product that you're producing. And you will have production schedules; they will have to be met, so you'll have to make it up later.
Yeah, maybe just to build on that a little bit, is there things they can do that if they got paid enough, they'd be able to do some amount of reduction in load during certain periods, or shifting in load, I guess?
I think from a chemical engineering perspective, certainly, and if we're thinking about the chemicals industry, for example, you would start to worry quite a lot about safety at that point. You're getting into fundamental redesign of systems.
Okay, thanks, Brian. Another question around the kind of large rotating mass, and have you looked at how widespread variable speed drives will be versus those that actually have the spinning mass? And is that going to be are they going to be able to provide some of the kind of inertia or services, I guess?
Yeah, that's a really interesting question. I mean, the short answer is no, I haven't, but you're absolutely right. If these drives aren't available or aren't part of the landscape, then this option goes away.
Yeah, and I think obviously there's a larger question there around how we ensure stability and use controls in the future. Gets into some of the other discussions we've had at the DC around grid farming and other things that maybe a broader discussion, but certainly of interest as well. Looking at hydrogen back to the grid, any discussion of kind of combustion turbines versus fuel cells? Is it really about making lower capacity costs, or is there any other kind of considerations there?
Yeah, so that's really interesting. I've looked at that a little bit, and so what comes out almost everywhere in this conversation is that you've got to drive down the capital cost. That's the one thing that you don't want to have sitting around on your balance sheet when your capacity factor might be lower. So completely agree with Brian's point there. And then the other thing that then becomes quite interesting is the ownership model. So if there's hydrogen being, for example, centrally produced versus locally produced, so if you have to own both the turbine and the hydrogen production facility, or just the turbine, again, that starts to change things.
That makes sense. Certainly something we can maybe get into a little bit more in the paper than we maybe currently have. When we think about the electrolyzers, and the next question is around the value that or the oxygen produced. Is there some could that boost the efficiency in some way?
Yeah, I'm personally quite enthusiastic about that. So obviously oxygen is an important industrial gas, and again, location dependent and so on and so forth. But yes, absolutely. I'm not sure that it would necessarily boost efficiency, but it could provide an additional revenue stream.
Is that something you've seen already or aware of, or is that still kind of more of a potential future value?
Well, I mean, you're obviously limited by the extent to which the electrolytic hydrogen is deployed, right? But it produces very high quality gas, oxygen at pressure. So absolutely, yeah.
Makes sense. And there's a few that kind of just scanning down some of the other questions around kind of with the intensive industries, heavy industries. There's kind of the policy type questions, and how do we actually support the development of flexibility strategies? So I guess kind of getting at the same, and even maybe later on, there's actually questions around kind of the engineering side of that as well. But are there ways we can get more flexibility if that becomes a policy kind of driver? And then the other specific question there around trade policy for the trade exposed sectors, how does that fit in?
I mean, so I think that, again, I think we need to distinguish carefully between the flexibility potential of the incumbent industrial base and the flexibility potential of facilities that are being designed and deployed in the coming years and decades. I think that the extent to which the incumbent systems are flexible is really quite limited, and limited by as much as the process design, as somebody else has alluded to, but also the type of control systems that are available. So I think that's something. And then when you then get into the policy space, I think what you would need to do would be to quantify quite robustly the value of flexibility by, of either existing incumbent systems or new design systems, and understand what that value looks like relative to its cost and relative to the cost of a set of plausible counterfactuals. And then you certainly could think about developing policies for that. Something analogous to capacity auctions could work well.
Yeah, I guess, does that get into how much that flexibility then can be provided by other things as well, that the things that are on the power system side, and then it just becomes a case of what's the most cost effective totally, and what can actually participate in the market. So
exactly.
Is there anything you have on trade policy? Is that something you've thought about?
So where is exactly the question?
It's in the first question there, trade policy for trade exposed sectors.
Yeah, well, I mean, it's vital, I think, is the short answer, right? I guess, and again, this is so A, it's vital. B, it's really interesting. So it's not obvious that, for example, one country like the UK could just decide, right, everything that we need to make in the UK is low carbon, and we will use it all ourselves, and that's fine. We're probably just not a big enough market for this to make sense. But in a world where, for example, you could imagine Europe, the United States, and maybe a few other major economies saying, this is what we want to do and we will trade on that basis, then a lot of this goes away. So I think it's as much, it's just massively inbuilt with trade policy, making sure that it doesn't, turn into some kind of sanction, I think is key.
That makes sense. Yeah. So and the next one kind of gets back to some of the kind of flexibility aspects again, the operating parts of the supply chain seasonally, and kind of having this almost seasonal storage, seasonal shifting of demand. Is there, I know it's been talked about a lot kind of from that power system side, let's say, as being something that we could really use, but is there some thoughts on the industry side around how to actually look at that?
Yeah, so I mean, I think that's really interesting, right? Because in some ways it's moving away from the just-in-time paradigm that we currently live in, right? And you're not talking about potentially stockpiling very significant amounts of stuff, so warehouse space becomes hugely valuable. I think it's not something that anyone's looking at terribly seriously, as far as I'm aware.
Okay.
They didn't see any of it in the literature that I've been reading in the context of our studying.
Is that something again where the kind of value aspects need to be quantified and then figure out how to?
You certainly could, but again, you're talking about having, in theory, a lot of dead money sitting around in widgets, right? So I think it's as much capital allocation as anything else.
A couple of quick questions. What around the average efficiency for the power to hydrogen to power? Is there any numbers there that are typical at the moment, and what might be achievable by 2030, 2035 is probably more interesting than current processes?
There are, but they escape me at the moment. I'd rather not say anything because I'll just be.
That's a good plug for the paper as well. I think we'll have some of those types of numbers in there. The next question that Ross asked, I think, kind of gets back to what we were just talking about a while ago around the flexibility as a function of engineering, and I don't know if there's any good examples of that are starting to come up. I know, looking at things like the European Horizon research projects that have just come out, there's a few that seem like they could be relevant to that in terms of being able to get flexibility from industry. But is there any good examples there?
Not off the top of my head, I'm afraid, no.
I see Brian had just on that paper, and Niall and myself are working through a draft. We'll probably share with that larger team, but we definitely want to get feedback from the broader EC community as well, and so we'll try and share that out if folks are interested. Send myself or Ryan Willis or whoever a note to let us know, and we can kind of add you to a mailing list so you can get a look at a draft before we actually finalize it there. And I think the idea is to have it finalized in the next couple of months anyway, but do be useful to get some input from folks that have interest in it. And excellent around that other business models for other than production of green hydrogen. Is there other discussions around demand response, energy storage? Is that something that you've been looking at?
So unfortunately not. I'm just an engineer. I don't get into business models too much.
Yeah. The cost of electrolyzers, the kind of experience curves, and what's your take on that? I know I've seen a variety of different cost trajectories that people have out there. What I guess, rather than specific numbers, what are the kinds of things that will result in lower costs other than just deployment, I guess? But
so I think that just maybe to take a slightly different tack on this. So I know there's a lot of enthusiasm and expectation that electrolyzers will become much cheaper, but I guess my response to that is yes, obviously costs will go down with scale up and experience and so on, but a very significant amount of the cost of producing electrolytic hydrogen is not just the electrolyzer stack, but it's also the balance of plant, and those components are very mature and widely available. And then moreover, you need pretty high quality water, which often needs some kind of upfront treatment as well. So there are a lot of cost elements in an electrolytic hydrogen facility that I think will not become as cheap as people are expecting. So that would sort of, in my mind, dampen the enthusiasm here. And there was a great paper that came out of MIT around just trying to understand it was in the context of batteries, and learning will only buy you so much. Learning will only buy you so much, I think was the name. And the conclusion was, well, when you break down the process to produce a battery into all of its constituent elements, actually the scope for learning is not as great as some of the more optimistic contributions to the literature might have you believe.
But when you look at those high renewable scenarios and seasonality, I think getting back to that aspect, and Nick has that question, you probably answered it already, but kind of the biannual cycling aspects there, is there, I guess, first of all, how feasible is it, and then secondly, how, even if it's feasible, is it likely? Is kind of, they seem to be the two ways to look at it, right?
Well, so if you think that you're some form of industrial process, and your job is to produce widgets of some type, and you're being asked to change the way you produce widgets and increase the amount of capital that you have sitting around not being paid off in the widget factory, but also to buy a warehouse of widgets. And you can do all of this in order to provide some energy balancing or whatever to the electricity grid. To me, that's a reach, right? And I would be surprised if that was the cheapest way or the most cost-effective way to achieve that outcome.
So it kind of gets back again to the concept of kind of quantifying the need for and value of some of these things, what the other resources, and I guess if it does turn out to be the cheapest way to do it, then it's possible, right? It's just more.
Sure, I mean, but you then get into this interesting world where, let's just say yes. I mean, I think the challenge is we need to go and quantify this and understand, what the actual results are.
Makes sense. There's some more kind of specific questions that I think we can answer in the short email that we're going to send out. Mm-hmm. So maybe just finish on Brian's one here, the synergies for, are there synergies for across both of these things, the excess oxygen to boost efficiency of thermal processes?
Yeah, so I'm quite enthusiastic about this. So the idea of increasing I mean, because basically what you could sort of do, and again, I like this idea of sort of co-locating and perhaps integrating a green hydrogen process or something with a thermal process, and you would translate your thermal process to something approximating an oxy-combustion paradigm, and then you'd produce a higher concentration CO2 stream at the back end, which could be purified, and you'd produce a CO2 storage ready stream. And so you derive a value from the oxygen that is co-produced with the hydrogen. So personally, I think, Brian, that's a good idea.
Okay. I do see we're at the top of the hour here. There's a few other questions. Apologies, we didn't get to all of them, but obviously a lot of interest. And there's kind of two things. We'll be sending out the video with the recording here, as well as answers to the questions that we haven't yet answered. I also will say that we'll take some of these kind of questions and comments and bring them into the larger paper. And so for folks who gave their name, we might end up following up with you a little bit to discuss some of the topics as we're finalizing that paper. So again, thanks very much, Niall. Appreciate everyone's input and feedback, and we'll be talking to everyone soon. I think there'll be more webcasts obviously coming up in the next month or so at ESIG, and otherwise we look forward to the in-person meeting in late October. I'll get together again. Thanks, everyone.
Wonderful. Thank you very much, Aidan.